This is the second of a couple videos on IR spectroscopy. In the previous video, we talked a little bit more about the theory behind IR spectroscopy, and in this one, we're going to be a little bit more practical. Now, I'm going to share with you some tips that I use in analyzing spectra. Now, there aren't really any hard and fast rules about analyzing IR spectra, and I'm not trying to assign every little peak. Instead, what I'm looking for is general recognizable patterns. Now, originally, I was going to have some example problems along with sort of the patterns that I look for, and I decided to split that into two videos. So in this video, I'm going to share with you the patterns that I look for, and then I've got a third video where we look at some specific examples that are going to be pretty similar to what I might ask on a quiz or a test. So I've made myself kind of a cheat sheet for things that I'm looking for when I'm analyzing an IR spectra, and I'll post this on D2L. The first thing I always do is draw lines at 1500 wave numbers and 3000 wave numbers. Right, and so for the line at 1500 wave numbers, I generally ignore the fingerprint region. And for the examples that we'll see, at least initially, we can generally do that. So I'm not going to look at the fingerprint region. Instead, I'm going to focus on the diagnostic region, which is above 1500 wave numbers. Right, and then the different regions of the spectra where I'm looking for peaks. Right, double bonds should appear in the 1600 to 1850 range, and generally looking for carbon-oxygen double bonds and carbon-carbon double bonds. Now, in general, the CO double bonds are going to have really high intensities. The carbon-carbon double bonds are going to have somewhat lower intensities. And usually, the CO double bonds will be at higher frequencies than the carbon-carbon double bonds. This doesn't happen much, but there were a couple examples in the book where they were comparing two different compounds that had carbon-oxygen double bonds. And if resonance is possible, that tends to weaken the carbon-oxygen double bond, and that'll shift it to lower frequencies. And then triple bonds will show up in the 2100 to 2300 range. All right, and then the line at 3000 is key. There will almost always be absorptions just below 3000 wave numbers, and that's due to carbon-hydrogen single bond stretches. And most organic molecules have carbon-hydrogen single bonds, and so there's almost always a peak there. If we have an alkene, the hydrogen attached to one of those alkene carbons is a little bit above 3100 wave numbers. And then if I have an sp hybridized carbon, that CH stretch is going to be even higher still. So this line at 3000 wave numbers divides the sp3 hybridized carbons, which is most of them, and if I see peaks somewhat above that or a little bit higher still, right, that's evidence that there may be an alkene and an alkyne, and I can pair that up with whether I saw a double bond stretch or a triple bond stretch at lower frequencies. And then I also am looking for other X here, meaning generally, in our purposes, oxygen or nitrogen stretches. So we'll see some examples. The OH stretches are a broad peak around 3300 wave numbers, and they're very recognizable. Similarly, carboxylic acids have a very broad peak around 3000 wave numbers, and they're generally pretty easy to spot. And then we'll look at some examples of amines, the difference being if we have an NH2 group, that's going to be a double peak, and if we have an NH group, that's going to be a single peak. Now, I'll give you a chart, either this exact chart or something like this on the quizzes and the tests that sort of have these frequencies listed. I'll be honest, I'm not really sure how helpful it is. Sometimes it can help to look, but really, I'm looking for these general patterns. And the fact that an OH stretches between 3200 and 3600 wave numbers store a lot of other things, and so this doesn't tell me what the shape is, and so that's why I'm not necessarily sure how helpful this chart's going to be, but you will have access to it. Right, and so let's look at some examples of the things that I'm looking for. So when I see this broad peak, sometimes I hear this described as a sword. Right, this is a dead giveaway that I have an OH stretch. It's very recognizable. All right, similarly, carboxylic acids are very recognizable. When we have a hugely broad peak centered around 3000 wave numbers, that's almost certainly a carboxylic acid. And sometimes people describe this as a hairy beard, right? Because where the carboxylic acid OH stretch overlaps with the CH stretches, right, we sort of get this, the hairiness of the broad peak. And then also because carboxylic acids, not only do they have the OH, but they also have the C double bond O, right? We're also going to have a carbon-oxygen double bond. It's going to be a very intense peak in this double bond region of the spectrum. In this case, around 17, a little bit more than 1,700 wave numbers. All right, the reason we draw that line at 3,000 wave numbers is to differentiate between the different types of CH stretches. So when I have an sp3 hybridized carbon, right, those CH stretches come out below 3,000 wave numbers. If I have a carbon-carbon double bond and there's a hydrogen attached to one of those carbons, right, that CH stretch is a little bit higher in frequency than the sp3 hybridized carbons, and so that shows up, generally around 3,100 wave numbers. And then if I have an alkyne, right, where we've got a carbon-carbon triple bond and there's a hydrogen attached to that, right, that shifts to even higher frequencies, somewhere around 3,300 wave numbers. All right, I mentioned on that cheat sheet, we can recognize differences in different types of amines. So if I have just a single hydrogen attached to that nitrogen, we get a single peak. If I have a double peak, also at about 3,300, 3,400 wave numbers, right, that's an indication that I've got an NH2 group. All right, and here's just another example of amines, right? So I've got the double peak, right? So this tells me, right, this is probably due to an NH2. In this case, this single peak, right, that's due to an NH, where that nitrogen's got two other bonds to carbons or something else. All right, and finally, when we look at double bonds, so when I see really high intensity peaks in the double bond region, in this case about 1,700 wave numbers, right, that's a dead giveaway that this is a carbon double bonded to an oxygen, right? And then this lower intensity peak at slightly lower frequencies, this is probably a carbon-carbon double bond. Now, if there are H's attached to either one of these carbons, then I would expect, right, a peak slightly higher than 3,000 wave numbers, which I see, right? So these are my CH stretches from the sp3 hybridized carbons, right? And this is the CH stretches coming from that alkene. So oftentimes, recognizing alkenes is noting both the double bond stretch and then the sp2 hybridized carbon-hydrogen stretch that comes out a little bit above 3,000 wave numbers. All right, so in the next video, I look at some specific examples where I will have a group of molecules and a group of spectra, and we've got to assign each spectra to each of the different molecules.